Okay, let's start. All right. So today we're going to finish our lecture on regression and proceed to talk a little bit more about p-values. So we'll see what I want to talk about p-values, but let's first continue from last time. Now, last time I introduced the idea of linear basis function regression. The first one we ever encounter is the piecewise constant model. The piecewise constant model, as you remember, looks something like this, right? Okay. So we're breaking down our x and y. The idea is traditionally we do mostly our so-called global regressions where the same exact relationship governs x and y regardless of the region of y, regardless of the region of x. But in piecewise constant, I'm going to break it down. I'm going to break x up into several different regions. In each region, I'm going to fit a constant. That's a piecewise constant model. Okay. How do we express this in terms of mathematical models? Well, I can write y equal to phi 1, beta 1, phi 1 plus beta 2, phi 2 plus beta 3, phi 3 plus a mean. I can write it this way. And each phi, of course, is a function of x. So for this phi 1 is equal to 1 in this region, right? And equal to 0. So for phi 1 is equal to 1 in this region and equal to 0 in all the other region of x. For phi 2, it's 0 here, 1 here, and 0 here. And for phi 3, it's like this, right? So each phi is a function of x that is equal to 1 or 0 depending on the region of x. And we call this phi basis function. Okay? So these are called basis functions. And so this is called a linear basis function model because the model is linear in the basis functions. We can also say that to go from x to phi x. Actually, let me first write a large phi is equal to phi 1, phi 2, phi 3, right? I'm going to define a large phi equal to phi 1, phi 2, phi 3. Then, essentially, I can write in this model in a very familiar form, which is this large phi, okay? And beta, right? Okay? This beta is basically beta 1, beta 2, beta 3. It's 3. This is 3 times 1 in this case. And this large phi will be n times 3, okay? Because there are n data points, 1, 2, 3. Now, if we write it this way, then obviously you can see that how do I can immediately see the solution to this system, the beta hat, is the formula or less formula. Transformation from x to phi. Now, phi is a function of x, right? The transformation from x to phi is called a feature transform. Essentially, we're changing x into something else. So we do a feature transform into a linear model again, and we can estimate the beta. Of course, the basis function doesn't have to be 0, 1. In piecewise constant, it's 0, 1, 0, 1. But we can, of course, not only fit a constant in each region, I can fit a polynomial in each region. I can fit, or maybe I can fit a linear function, right? So fit a linear function here, a linear, and another linear line here. That's called a piecewise linear model. And similarly, just like constant model, I can express the piecewise linear model in terms of this linear basis function setup. When we do piecewise linear, like we mentioned last time, sometimes we do not like something like this. Okay, we do not like the fact that there are all these linear functions that are disjoint, that are not continuous. It is often preferable, and I will talk about why it's preferable, but it's often preferable that we link these together to make a continuous function in terms of our final output. All right. So what can we do is we can require these two linear lines to be the same value at the boundary, and that just means imposing boundary conditions. In the simplest case, when we have two regions, one cut point, two regions, then I have one linear function, the other linear function in the region. I simply require them to be the same value at a boundary. that reduces one parameter to estimate, right? One less degree of freedom. So in the end, 1, 2, 3, 4, we start with four parameters. We impose a condition so that we end up with 3 parameters to estimate. And you can very easily, you can do this yourself, but it's very easy to derive that from these 2 equations, you can derive, plus the condition, you can derive that the final relation is something like this. Okay? It's y plus so if we cut our region into 2 parts, and I will let this part be C, this is the cut point, then I can fit a linear function here, I can fit another linear function, but if I require them to have the same value on this boundary point, so something like this, right? Something like this. If we do this, then we can write the whole function as y equal to beta 0 plus beta 1 x, just like before, but plus beta 2 x minus c plus. Okay. Now, what this function is, x minus c plus, is equal to 0 when x is smaller than c, and equal to x minus c if x is larger than c. So, in other words, this is a linear term that only kicks into effect after c, right? So before c, we have this linear line, and after c, you can think about if x is larger than c, we still have this linear, okay? We still have this linear curve. But then another linear effect kicks into it, right? So that changes this slope from here to here, which is the effect of beta 2. So this x minus c plus is defined in such a way. And what is this? This is essentially a basis function, right? It's just a basis function, phi x, because it's a function of x. So we end up with defining a basis function that is defined like this. And how do we estimate what is beta hat? Now beta hat here is beta 0 hat, beta 1 hat, beta 2 hat, right? And this is simply equal to the large phi prime phi inverse phi prime y, where the large phi is defined as a constant term, an x, okay? And our new friend is small phi x, which is equal to x minus c plus, okay? The function, right? I write it this way, then this is my solution for beta, and immediately I have all the solutions. So this is piecewise linear function. Of course, I don't have to do linear, right? I can do more. So let's think about a piecewise polynomial, 3rd degree. Now, if I'm going to fit a, let me find out where it is. There we go. Okay. I can fit a piecewise cubic polynomial. So cubic means 3rd degree. Now, if I fit a 3rd degree, this is the first case in which I just fit a cubic polynomial, 3rd degree polynomial in each region. I break into 2, 3 regions. In each region, I fit one curve like this. Now, that doesn't look nice at all. It's discontinuous. It looks weird. So the first thing I'm going to do is that just like in linear model, I'm going to require their value to be the same at a boundary. So I do that. Okay. So in this case, it is continuous. It's the boundary is the same, but that still doesn't look very nice. If you look at it, that has this kink here that just looks weird. So I'm going to do more. Not only do I require this curve to be continuous, I will require it to be smooth. And by smooth, I require not only the value of y, predicted y, to be the same at this boundary, I require the derivative of this curve to be the first derivative and the second derivative to be the same at a boundary. That makes the curve looking smooth. So this is the first derivative being the same at a boundary. And here, because this is a 3rd degree polynomial, I can go to second degree degree derivative. So here's the second derivative being the same. And if I impose this condition, then you can see the green curve, which is our final output, looks very continuous and smooth and looks pretty good. Okay? So this is what I'm going to do. When I do piecewise polynomial, I'm going to require not only the y being continuous, the value to be the same at the boundary, I'm going to require the first derivative and the second derivative to be the same at the boundary to make it really smooth. Right? So instead of looking like this one, we'll end up looking like this very nice output curve. How do we do it? It's very simple. Basically, let's imagine again, there is two regions, right? There's a C, but we're dividing our x into two regions. I'm going to fit a third degree polynomial here and a third degree polynomial here. But so the equation look like alpha 1, 0, right, all the way to alpha 1, 3 x third. This is a third degree polynomial in the first region, and then that's the third degree polynomial in the second region. But then I'm going to do more, right? First of all, I require these two to be the same value at the boundary. So that means here, okay? So that means, okay, at x equal to this, this C, let's just call it C, right? So x equal to C, the first region give me this one, right, this value, and the second region will simply give me alpha 2, 0, because everything else becomes 0. Okay? So that's my first condition. The first condition is they are the same value here. The second condition is the first derivative being the same at the boundary. So I'm going to take a derivative with respect to x and put it at a boundary, and take a derivative with respect to x, put it on the boundary. That's our second condition. And then, of course, I go to the third condition, is the second derivative is also the same, which is taking one more derivative with respect to x. That gave me the third condition. So 1, 2, 3, three conditions for piecewise cubic polynomial. So how many parameters do I have in the end? What is the degree of freedom? How many parameters do I have to estimate? For each cubic polynomial, we have third degree polynomial, right? We have 1, 2, 3, 4. We have 4 parameters to estimate for third degree polynomial. Okay? P plus 1. So I have 8 parameters to estimate from these two. But then I have 1, 2, 3, 3 conditions. So that gets rid of 3. So in the end, how many? 5. Okay? We have 5 parameters to estimate in the end. And turns out that in the end, I can write my final model very similar to this one. I can write it this way. Y equal to beta 0 plus beta 1 x plus beta 2 x squared plus beta 3 x cubed. So that's exactly the same as the first region, right? The first region. But now I have the second region. But it turns out that once you impose the condition, the 3 conditions, in the end, the whole thing can be just written as beta 4 x minus c. I'll just write c, right? C to the q plus, okay? You can just write out this one. So you can do the derivation yourself, but it's pretty easy, okay? So in the end, we just simply add another one onto this. Basically, we have the same cubic polynomial, but after passing this threshold, we have another additional third degree effect that changes into something else if after imposing these conditions. And what is x minus c to the q plus? What is this function? Again, this function is defined as being 0 if x is smaller than c, and being x minus c q if x is larger than c. Okay. That's what the plus actually means. All right? Okay. So we can just write it this way. And you can see if we write it this way, how many parameters do I have? 1, 2, 3, 4, 5. These are the 5 parameters that I want to estimate. Okay. So it turns out that a degree D spline, this is called a spline. Right? The piecewise polynomial model is also called a regression splines. Spline is a word we hear a lot. There are different kinds of splines. The spline that we're doing here, regression spline, is essentially a piecewise polynomial. So a degree D spline is basically a piecewise degree D polynomial. That's how it's defined. Now, so here we have the third degree polynomial piecewise. Then we have the third degree spline, essentially, or cubic spline. That's the way we call it. In general, if we have a degree D spline with essentially n regions, okay, so So here we have two regions. If we have n regions, and now in each region we fit a degree d polynomial, then together how many parameters do I have? Together we have d plus m parameters to estimate. So here we have two regions, so m equal to 2. D, we are fitting a third degree polynomial, so d equal to 3. So in the end, how many parameters do I have? I have 5. Okay? So that's the 5 parameters we're estimating for this third degree piecewise polynomial model, or third degree spline, cubic spline. Okay. And let's again go to this wage data. This wage data probably is not the best data to demonstrate the power or the effect of piecewise models like piecewise constant or spline regression splines. But here what we're doing is we're doing a cubic spline, is the third degree piecewise polynomial, and we're dividing our data into 1, 2, 3, 4 regions. So a 3-cut. Each region I'm fitting a third degree polynomial. So each region does a third degree. It looks very smooth, and because we're requiring everything to have the same value being continuous and smooth. Okay, first degree, second degree being the same. So it looks entirely very smooth throughout the entire region. The way to do a cubic spline in R is surprisingly easy. All you need is to invoke to basically require the splines package and use the spline library, and there's the function here is BS. Okay, so BS is the spline, is a cubic spline where we're regressing wage on H with knots. So the knots means where you cut the data, right? So here we cut our H into into 4 regions. The 3 knots are 25, 40, 60. So here is what it looks like. Here we go, right? This is 25, 40, 60. That's our 3 knots. With these 3 knots, we're dividing data into 1, 2, 3, 4 regions. And in each region, we're fitting a degree equal to 3 cubic polynomial. Okay? So that gives us a cubic spline. Very, very simple syntax. And if you look at the results, that this is the estimated parameters. So we have, how many parameters do I have? We have 1, 2, 3, 4, 5, 6, 7. We have 7 parameters we have estimated. Why 7 parameters? Because we have a cubic spline and we're dividing into 4 regions. So third degree polynomial plus 4 regions, that gives us 7 parameters to estimate. Right? So that's why you see the 7 parameters there. Now it turns out that oftentimes what happens is in this region and this region, these two are called boundary regions because they are at the end, right? So this is the left-hand region, this is the right-hand region. In these regions, it turns out that oftentimes the cubic spline will give us something. Look at this, right? Something like this. Okay. So this is a cubic curve, right? A cubic polynomial, and a cubic polynomial. If we want to go beyond this region, if we want to extrapolate to predict some value beyond this region, sometimes it will give you pretty sort of outlandish predictions, right? Okay. So if this is the boundary region, if this is our fit polynomial, then what if I want to know what happens, I want to make a prediction when x is here? Then according to this polynomial, it will go all the way to a very high value. If I want to predict x equal here, then it's beyond our blackboard, right? So in this sense, extrapolation, right, go beyond this range, using this polynomial can often lead to very wild predictions. What if we're in sample within this range? That's okay. If we want to go outside, then the higher degree polynomial often give you very unstable results. So what do we do? Well, sometimes if we care about, we want to generate more stable predictions beyond the range of observed data, we do not fit a high degree polynomial. Instead, we just fit a linear model. Okay, just fit a linear, because the linear model, remember, it's more stable. It has generally a better generalizability because it's a simple model. So the prediction sometimes is is better, right? So what we're doing is, instead of fitting a high degree polynomial in this boundary region, we can instead fit linear model in the boundary region, but only in the boundary region. So inside, I can still fit a third degree polynomial, fourth degree polynomial. But at the boundary, let's be linear, so that our prediction is more stable beyond the boundary. That's the idea. If we fit a third degree spline inside, but fit a linear model at the boundary region, that's what we call a natural spline, okay? Natural cubic spline. The idea of natural, why call it natural? I don't know, right? But the idea of a natural spline is replacing the high degree polynomial at the boundary with a linear model to potentially have more stable prediction outside of an observed range. That's called natural spline. And in R, if you want to do natural spline, again, extremely easy. You just replace the BS with the NS, okay? Natural spline, age, specify the knots, and there you go. Okay? All right, so that's the idea of regression spline or piecewise polynomial model. And as we discussed, it is a model that is so-called local or non-global model because essentially the relation changes with different region of X. And it's more, as you can see, it's more flexible than a global linear regression or polynomial model, right? Because we allow the relationship to change between X and Y to change in each region, potentially delivering a better predictive performance or better fit to the data than a global model could. But then there's always a problem. The problem is how do we, I don't know if it ever occurs to you, but the problem is how do we decide where to cut the data, okay? So here we're dividing the region into 1, 2, 3, 4, 4 region, but why 4? Why cut that 25, 40, 60? Sometimes the cut makes intuitive sense, or theoretical sense, in the sense that you know the relationship from your outside knowledge, right? Using your expert knowledge. You know that the relation should change when age below 25, between 25 and 40, right? So in this case, 25, 40, and 60 could be a pretty good cut. Because from our experience, we know that people, using outside knowledge, we know that people below 25 are kids, right? Like you guys, that that have not really started or just entering labor market. So that's kind of one relationship. Between 25 and 40, it's like you're the first half of your professional career, 40 and 60, the second half of your professional career, and then retirement. So it's a natural way to cut your X into different regions. But oftentimes, we do not really have that. For many data, you don't have a prior knowledge. You don't have some other knowledge to guide you how to cut your data. Then the question is how to cut and how to divide them into different regions. And also, why even in this case, right? Why only 4? Can I cut every 5 years? Okay. 25 to 30, 35 to 30 to 35, 35 to 40, or maybe even 1 year, right? That doesn't work. But can I just cut many? Isn't it true that the more I cut into different regions, the better my fit will be? Well, it's true that the more you cut it, okay, you divide it into more and more regions, the more your in-sample error is going to decrease, right? So we cover this again. The ideal is the more you cut, the more your model, the more complex your model essentially becomes, right? Because you're fitting a different relationship in each region, your model becomes more complicated. Even if we have a lot of boundary conditions, your model still becomes more complicated. In the case of cubic spline, the more you cut, the more terms you add, right? Okay, so here's one cut, we have add one term, second cut add another term, third cut add another term. So every time you make a new cut, you divide the data into more regions, your model becomes more complicated. And of course, you are going to fit your existing data better because as the model becomes more complex, you are going to decrease your E in. But your E out may not decrease, right? It may first decrease and increase. So the question of how many to cut actually is the same question that we have been asking in the introduction, which is how to find the optimal degree of complexity for our data. Now, when we discuss regression, piecewise regression model, we assume that you come to the model with a predetermined set of cuts. You know how to cut it. You tell the data how do you want to cut it, how many regions you want. We assume that. Now the question is there any way to not assuming any cuts, but let the data decide how many cuts is optimal? Is there any way to do that? The answer is yes. Okay? There is potentially a way to, without knowing how many cuts you want, just use the data to tell us how many cuts you want. Maybe just one cut, maybe no cut, maybe numerous cuts, okay? So there is a way to do that. And if we, especially for piecewise constant, if we fit a piecewise constant model, but we do not know how many cuts we want, we let the data to tell us. How do we let the data tell us? We try to find the optimal number of cuts that give us the minimum E out, okay? So we'll try to do that. Find out the best complexity. Let the data tell us how many cuts. If we do that for piecewise constant, then we will arrive at a very famous model in statistical machine learning called a decision tree. Okay? Tree model. I'm sure people have heard of it. Right? People have heard of it, decision tree model. So a decision tree essentially is a piecewise constant model. But instead of you tell the model, you tell the data how many cuts you want. It is the decision tree is automatically finding out how many cuts you want. Okay? Try to find the optimal degree of complexity. We will discuss decision tree later in this course, not today, but this is just like an appetizer. Okay? All right. Now, so far, in the model we have discussed, we only have one x and one y. So x is one-dimensional. When x is one-dimensional, it's easy to cut it and fit different relations in each region. What if x is two-dimensional? 3, 4, 5. What if we have high-dimensional x? Do we do the same? Can we cut in 2 dimensions, 3 dimensions, 4 dimensions? Yes, we can, okay? It's a little bit harder, but yes, we can. But we can also do what? We can also assume that when we have multiple dimensions, we can also assume that each dimension is independent. And, not in the sense that not independent, but we can also assume that each dimension's effect on y is additive. Now, if we assume additivity, then that makes our job much easier because we can independently cut in each region and then just combine them together in an additive way. So that brings us to generalized additive models, GAN. A GAN is a model where suppose our x is multi-dimensional. So we have an x that is essentially x1 all the way to xp. Okay? That's p different x variables. Now, how do we model them? The GM model is a generalized additive model. Its additive model means we assume the effect of x1 on y and the effect of xp on y is additive. So we can write y equal to omega 0 plus, just use omega, but you can use whatever. Use omega 1x plus omega 2x. Sorry, 1, okay? Actually, let me write it this way. Suppose we say y is equal to beta 0 plus beta 1, x1 plus beta 2, x2. Okay? Plus beta p, xp. Now that is basically linear regression model, right? You're all familiar with. I think that's sometimes called a multivariate linear regression, or whatever, right? We'll have more than one x variable, more than one dimension. So I can generalize this. I can say instead of beta 1 times x1, I can let this be a function of x1. Okay? So I can say this is omega 1 x1. Well, let me just use phi, right? I think phi is probably more familiar to us now. I can let this be a function of x1. And I can let this be a function of x2, right? So each thing is, instead of just x1, x2, I can let this be a function of each x. But this is a function only of x1. and this is the function only of x2. So in that sense, it's additive in the sense that the effect of x1 on y and the effect of x2 on y is linearly combined, right? They're additive together, even though each one could be a nonlinear function. That's called general additive model. Okay? And this is actually a feature transform. Right? We're transforming x1 into this, x2 into this function, x3 into this. Now, what is this function? What is this function of x1? Well, it can be anything. At the simplest, it can just be x1. Next, that's a linear regression. Or it can be x1 plus x1 squared. That's a polynomial. Or this one itself could be a piecewise polynomial, piecewise constant. Right? So in x1, we're going to break it up. I'm going to fit a polynomial here, 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 right? A sort of regression spline for x1 only. So for each dimension, I can do whatever I want. As long as I add each dimension up in an additive way, that's a general additive model. Example, okay? Suppose I'm trying to predict wage, again, but now the variable is not only age, right? We'll be doing wage and age. But now I do wage, age, education, and a year, just time. So my y variable is wage, but my x variable has 3 x variables. The first x variable is age, just like before. The second is education, and the third is what time it is, okay, what year it is now. 3 different 3-dimensional x. So what I can do is I can fit a different function on each different x and additively combine them. I'm going to fit a polynomial model for time, for year. I'm going to fit a natural spline for age. And I'm just going to fit a discrete sort of like dummy variable regression fixed effect for age, for education. So for each education level, I have a different constant, right? So that's a basic, I can do this for education, do this for age, and do this for year. In R, that's extremely simple as well. Education is a discrete variable. I can just put it here like this. And I'm going to natural spline for age. I'm going to do polynomial for year. And I'm going to add them together. Now, this final add them together is the additive combination in general additive models. So what this general additive model is saying is basically you can do whatever for each dimension. Each dimension becomes a function. And you can do whatever for that function. And we are going to additively add them together to become your final prediction. And that's it. Okay? So that gives you a lot of freedom to specify how you want to model the relation between x and y. What's important is for general additive models, we are still, in the end, getting our OLS solution. So this is very good, right? Because in the end, whatever we do in each dimension, suppose I fit a linear regression in dimension 1, a polynomial dimension 2, a piecewise constant in dimension 3, a regression spline in dimension 4. Even if I do that, in each dimension, essentially it's a linear basis function model. And if you add them all together, it's still a linear basis function model. So in the end, we can, no matter how complicated your model is, we can express it as y equal to beta times this large phi. And this beta will just be the OLS solution. Okay? Phi prime, phi inverse, phi prime y. You can basically get an analytical solution immediately. So it's easier to fit, right? Okay. All right. So let's talk. So that's so much I want to discuss in terms of regression models. In the end, let me discuss a little bit about generalization, okay? Because we start with the linear regression model, OLS, and I said that for the linear regression model, the VC dimension is small. It's if you have a p-dimensional x and a VC dimension p plus 1, so it's easily generalizable, right? But in the end, toward the end of this course, this lecture, I introduced more complicated models, the piecewise constant, the piecewise linear, regression spline, and the general additive being sort of the most general case, right? What about these more complicated models are no longer as generalizable as a simple linear OLS, okay, linear model. And so here's the trade-off, right? But before that, let me just say, I've already introduced the ideal of feature transform, that a typical linear basis function is a transformation from x to z, and the z is just big phi, okay? So I'm transforming from x to phi, but let me just call it z, okay? Z equal to phi x. So this is called a feature transform. So initially, if we express in terms of x, it's no longer a linear function. But if we express in terms of z, after transformation, it becomes a linear model again, right? Do you get it? So if I have y equal to beta 0 plus beta 1 x plus beta 2 x minus c plus, right? So this is a linear, this is a piecewise linear model, and this is nonlinear in x. It's linear in beta, but it's nonlinear in x. This is not a linear, why this is, no, this looks like this, x minus c. So it's a nonlinear function. But I'm going to transform it into z, right? I'm going to say, okay, beta is equal to beta 0 plus beta 1 z1 plus beta 2 z2 with the basic idea z1 is equal to x and z2 is equal to this. It's really simple, right? Z is our basis function, okay? Phi, just phi1 and phi2. Now, after transforming them into z, this becomes a linear model in z. They're always linear in beta, but it's not linear in x, but it's linear in z. Right, so this is basically the idea of feature transform. So after transforming the feature from x to z, I get a linear in z model, right? It's something like that. This is another illustration where suppose the relation between x and y is this sine curve, right? Okay, then how do I model the relation between x and y? Well, it's probably harder to model, but if I do a transformation, a feature transform, I turn x into a function of x. So let z be sine x. Then immediately I have a linear relation between z and y. And you can say, okay, y just beta z. The ideal of feature transformation. So once we decide on a particular feature transform, because there are numerous ways to do feature transform, right? The piecewise models that we have discussed so far, the regression splines and the general additive models, all these models can be expressed as linear basis function models. So in all these models, you can think about them as transforming from x into a phi, right? Into a new phi, and then this phi becomes our new model, or this z, right? Whatever you call it. Okay. So all these complicated models are essentially linear basis function models, just with different kinds of transform. Some transform give you a simpler model. Some transform give you very complicated models. The question is, again, how well do they perform in terms of out of sample performance? Okay, in terms of the underlying true error that we care about. We have the same generalization approximation trade-off, just like we introduced in our introduction. The ideal is, once you do the feature transform, once we transform from x to this phi, then our model becomes this, okay? Our model becomes this h phi, which is in this model, every hypothesis is beta z, right? It's this linear hypothesis. But this z is already transformed. Now, for this model, I can calculate its VC dimension. And this VC dimension is going to be different from the original VC dimension of beta x. Right? So we have a beta x, that's our model. And the VC dimension for this one is simple, it's just p plus 1, depending on the dimension of x. Once we transform this x into another phi, okay, using a feature transform, for example, this phi could be x and x squared. That's just simply transform x into a polynomial model. Now, once we do this transform, our VC dimension is the VC dimension of this new model, where this model is the transformed model. And this transformed model is going to be more complicated, typically. Right? So the VC dimensions go up. Right? Okay. So in the end, the sort of the inequality we have in the end is the E out is smaller than E in. Well, this is our familiar VC inequality. And the only difference here is the VC dimension here is the VC dimension of the transformed model, not the original beta x. Okay? So in that sense, we face exactly the same trade-off. which is if you transform X into a more complicated model, a more complicated transformation, then in the end, your E is going to go down. So the more complicated your model is, the E is going to go down, but however, your generalization bound is going to go up, right? So we have this familiar U curve again, right? So this is all old stuff, right? Now, what is interesting here that makes in practice, what makes things more interesting is that oftentimes when you approach your data analysis, many people do not set up. Many people before they do data analysis, before they analyze the data, they do not have a feature transform in mind. They do not say, okay, before looking at the data, they say, okay, I'm going to do a polynomial. I'm going to do a piecewise constant. No. They look at the data and then decide what kind of model they want to use, instead of before looking at the data. Right? For many people in practice, they don't do that. However, when I write down this VC inequality, I'm assuming that you have already determined what model you want to use, what kind of feature transform you want, what kind of nonlinear model you want to use before looking at the data. And that holds, okay? But if you decide on a model after looking at data, then things become more complicated. Because why? Because typically what people do is they will try one kind of transformation first. So they will try, for example, the basic linear regression first. And then they discover that it doesn't fit very well. Well, in that case, let me try the polynomial. So they try the second model. And then if the polynomial doesn't work very well either, they try the third model. So let's do a piecewise polynomial. That fits the data even better, right? So in the end, if the person chose a piecewise polynomial, it's the result of what? It's the result of fitting a linear first, and then a polynomial second, and then a piecewise polynomial in the end. So in that case, what is the true VC dimension of that person's model? Okay. Let's think about it. So suppose the person first choose a polynomial model. Okay, I try the linear, I try the polynomial model, and then I try a piecewise constant. Okay? Piecewise constant. Well, let's forget about linear. Okay, so the person first choose first try polynomial, and then try piecewise constant. And then he said, okay, I'm satisfied with this. Let me pick this as my final model. The question is, what is the generalization performance of this model? What is the VC dimension? Is the VC dimension the VC dimension of piecewise constant? So let this be HPC, okay, piecewise constant. Let this be HP, the polynomial model. The final VC dimension of he finally choose this model. So is the DC dimension the VC dimension of HPC? No, it's actually not. Because why? Because he tried this model first, and then tried this model. So in effect, the final hypothesis this person picked, yes, it's a piecewise constant. He finally picked a piecewise constant hypothesis. But actually, this hypothesis picked not just from this model, but from the combination of this model and this model, correct? Because he tried the hypothesis here as well. Just doesn't like it. And then tried this model. So in the end, the hypothesis he finally picked is chosen not from this model alone, but from a combination of HPC union, okay, and HP. This is actually the true model that he's picking his hypothesis from. Remember, any model is a set of hypotheses. So the polynomial is a set of hypotheses. Piecewise constant is a set of hypotheses. You pick one hypothesis in the end. And that hypothesis happens to belong to this set. But when you're picking it, you also try this set. So in effect, the final hypothesis you picked actually comes from the union of these two sets. You're in effect tried all of them. So in other words, your VC dimension is going to be higher than larger than the VC dimension of piecewise constant model alone, because it's the VC dimension of the combined set. You are in effect trying a more, in fact, estimating a more complex model than what you get in the end. Okay. So what does that mean for the generalization ability of your model? It means that in the end, your final fit, your final hypothesis that you pick, the generalization performance is going to be worse than if you start with PC, if you do not try this. So you imagine there are two people, right? One person, one researcher, before looking at the data, decide I'm going to use piecewise constant. The other researcher look at the data, try the polynomial, and then try piecewise constant, and then finally pick piecewise constant. In the end, these two researchers may give you exactly the same hypothesis. Okay? But the second approach actually generates a result that actually worse, because they generalize worse. It has a worse generalization performance, because in effect, it's picking from a more complicated model. Your VC dimensions are higher. So this is a very, very key point. Okay? Right. Now this brings us to a practice that's often counseled against in data analysis, which is trying until you find a good fit. Right? I think many, I'm not sure when you take statistics class whether your professor ever warned you that it's not a good practice to try many models until you find someone that fit the best. And the reason why is if you try many things until you find what is satisfactory, that sometimes is called specification search or data snooping. And that's a very bad thing. Because when you try many things until you pick one that's good, you are in effect, you are picking your hypothesis from a combined set of many different models. And your VC dimension is going to be very large, and your final fit is going to have very bad generalization performance. It's not going to be very good. Now, intuitively, so this is all, right? This is, I think, based on the analysis, the VC analysis we have already introduced in our foundation lecture. But intuitively, it's also easy to understand, right? The more models you try, the more you're trying harder and harder to fit a specific data set, right? The more your final fit is, the less your final fit is going to be able to generalize to new situations, right? It's the same idea behind why more complicated model could give you a worse generalization performance, because more complicated model means a set that containing more hypotheses. So the more hypotheses you try, okay, in order to find out your best pick, the more you are trying too hard to fit existing data, the less your final fit is going to generalize very well. So the best practice, right, in all cases, the best practice is to decide what model you want to use before looking at the data, rather than after looking at data and try many different things and then finding out what works best. Okay, the previous one will give you a better performance in the end. Okay. All right, so that's it for our discussion on regression. And in discussing regression, I briefly touch upon the topic of p-values and hypothesis testing. So we discussed a little bit, right? So what I'm going to do now is going to have a special lecture specifically talking about p-value. Because p-value in reality, it's a simple concept, it's a simple practice, but in reality it's often misused very frequently in empirical research. And considering many of you do empirical applied research, I'm going to spend some time talking about the misuse and over-reliance on p-values. So that brings us to the next lecture.